All right, so thank you very much, Jeremy, for this introduction. Let me say my great pleasure to be here today. I'm neither a student nor a postdoc of Michael. I'm something even more. I'm another kind. I'm a predoc of yours. I was very fortunate that I could visit you in Bell Labs before my PhD. This was back in 99. I spent a year there under your direction. This was a very important time for me. This is connected to Princeton because it's Ingrid Debusches, you remember, who connected us. This was a very important time for me because I had no idea that I would be doing mathematics all day long. I mean, I've always liked to do mathematics, but after I graduated from École Polytechnique, well, I didn't know really what I wanted to do, and I didn't know that you could actually really do this job all day long. So I really needed to sort of get to learn the problems, get to learn the people, get a feeling of what was going on. And this is exactly what I learned in Bell Labs. And because this has been said, I mean, you've given us all the people that interacted with you. I mean, you've always given us lots of time. For me in particular, there's something else you gave me. You showed me beautiful problems. And this is something I'm very fortunate for because this is exactly what I needed, to sort of see and meet problems on which I could say, well, yeah, I can spend my time on this. I like it. I really do. All right, so let me explain what kind of problems you showed me because you taught me all the basis of this. So really what I want to discuss is this energy concentration phenomenon in nonlinear wave propagation. So really, this all starts with the nonlinear Schrödinger equation here. So I'm really seeing this, I'm thinking of this as my nonlinear Hamiltonian PDE. And I mean, we've seen this equation already. I'm really thinking here, so X is in RD, P is just my nonlinearity. And for the sake of purpose, I mean, what we're really doing here is trying to understand some model problems. So really, D and P are just parameters, and I'm going to allow myself to play with this guy. And what we want to do really is on these very simple type of problems, we really want to have a grip on the solution, sort of try to understand what solutions look like, what kind of behavior we should expect, and what we can say about solutions. So we've seen this equation already a bunch of times. I mean, so let me remind you that there are two fundamental facts about this equation seen on the whole space. Fundamental fact number one, conservation laws, right? I have two quantities that do not evolve in time, that are given to me, that are, of course, related to the Hamiltonian structure of my problem. These are energy, which in a focusing problem like mine with the plus sign has a minus sign here, so it's not a definite positive quantity. And there is the mass. And you should think that these are the only two information that I have for free, conservation of these two guys, okay? And then there is another fundamental fact, which actually is fundamental because the analysis says so, but it's not really clear maybe at first hand why this is so important. It's a so-called scaling symmetry. It's the fact that you have a symmetry group, actually a much larger one than just acting on the equation. And the symmetry is the following, is that if you give me a solution, I can form another one by just dilating here space and time. And then I need to do this in such a way that I renormalize my solution here by this multiplication factor. And this parameter p, 2 over p minus 1 here, is directly related to my nonlinearity here. So from there, it's become, it's a very useful thing to compute the so-called scaling exponent. So this is just a heuristic computation. If you want, what you do is you say, well, how many derivatives in L2 of my solution do not see the scaling symmetry? Right, so there's no reason why this should be a relevant number. It is a relevant number because it shows up everywhere in the analysis. But at first hand, why is this so important? It's not so clear. So you do your algebra, and you find that this number is d over 2 minus 2 over p minus 1. Right, so the typical, so if this is my critical exponent, right, so SC is d over 2 minus 2 over p minus 1. So the typical example is d equal 2, p equal 3. This is the cubic 2D nonlinear equation which we saw yesterday, in which case the critical space is L2. But I have, of course, all this possible range of S, and something that we know from scratch. So we call this is what we call the critical space. But the only point I want to make is that what we know now is that, and this is something you can say in very general, there are three kinds of problems. There are the so-called critical problems. The critical problems are SC equals 0. So this is mass critical. and this is energy critical. Right, so why is this problem critical? I mean, the fact that it's critical just refers to the fact that there is something very funny happening for these two values. So if you think that you fix dimension, say, and you say d equals 3, say, then for this two value of p, you have something very funny going on. You have the fact that your scaling symmetry, that is your group of symmetry that acts here, leaves invariant, say, for example, in the L2 critical case, it leaves invariant the L2 mass. Which means that when you dilate, when you renormalize your solution, this only a priori information that you have on your solution, well, it's completely invariant. In particular, even though this quantity is invariant, it can very well happen that your waves want either to concentrate or to be diluted according to this kind of transformation. Your only conservation law will not see it, right? So this happens to you, so the first, if you want, when you raise a nonlinearity P, this happens to you for the first time at SC equals 0. So this is this value here. Of course, SC, if you want, is a growing function of P. And when you raise P, well, then you hit the energy critical problem, which is SC equal 1, where the same thing happens to you, but now it's at the level of energy. So you have these two critical problems. Of course, you have all the problems in between. And then you have the so-called energy supercritical zone, which is what happens over there, and which is typically a place where essentially little is known at this point. So the very rough, very vague idea that you should have on this is simply the fact that essentially what's happening in the energy, you should think is the following thing. What's happening in the energy supercritical case is that in some sense, in some regimes, and this is exactly what's going to happen to us, the only two information that you have for free on your equation, that is mass, conservation of mass and energy, which are inherited from the Hamiltonian structure of your equation, these two informations are weak. They are really weak. I mean, here, for example, if you are here, well, above you, you are at the mass critical level, and you have a conservation law above you. This conservation law is very strong. It yields you, it forces a number of things. When you're above, and there are many problems which actually live here, when you're above, you have this really dramatic problem that the only information that's given for free is very weak. So you have to understand how to deal with this issue. So the problem of singularity formation that I'm going to discuss about, it has in some sense nothing to do with singularity formation. This has to do with the qualitative understanding of what solutions look like, and this is deeply connected to the soliton theory. So let me recall you very briefly what a soliton is. You know very well that in this equation, so typically, so it depends on the power of P here, you can propagate very special nonlinear solutions. So typically, for example, if P is not too large, you have time periodic solutions, U of T and X, of this form. So this is sort of a separation of variable in space and time. So in time, you just oscillate. And Q, so in this case, it's just the solution to this nonlinear elliptic equation. And typically, what you should have in mind is that Q is just some, so can I lift this? Yeah, well, I'm going to erase that. I'm just going to maybe. Q is a nice, well-localized profile. Right, so it's typically radially symmetric. Right, so Q is a nice guy. It's the ground state. I'm really going to talk only about the ground state, so use the unique up to translation, positive decaying solution to this equation here. So I have this wave packet that just propagate without any deformation. And again, so there is this issue. Sometimes they are periodic, and I'll show you situations where these guys, in fact, are stationary. And one thing that is very well known is that, and this is really, is that if you're here, solitary waves are stable. This is a zone where a solitary wave is stable, so this is SC negative. And I'll typically look in this zone, and in this zone, we know that the solitary wave is unstable, and precisely the way I'm going to address the question of singularity formation is precisely through the description of the instability of the solitary wave. So what can happen to you? Well, what can happen to you, again, is this so-called modulational instability of the solitary wave, is this fact that in these problems, you can start If your initial data is exactly the profile Q, well, you know what the solution is. It's just it will not move, essentially. But you can start very close to this guy, so typically like a ball like this, but at time, a very small perturbation of Q. At time 0, the size is of size 1. And for some reason that you have to understand, what happens to you is that dynamically, the solution wants to drift, and the size of the parameter lambda changes dramatically. It can go to 0. This would correspond to a focusing bubble. So this is singularity formation. Or it may want to go to infinity, say, for example, or it may want to oscillate forever. It may have transient regimes. It may do whatever you want. And this is typically the kind of phenomenon that you want to understand. And from this decomposition here, what you see immediately is the following thing. What we will try to do, and this is what we try to do when we compute solitary wave instability, we try to decompose the flow into two parts. There is an infinite dimensional part that is something that has to do really with the infinite part of the solution. So it's hidden here in this little perturbation. That is, on my solitary wave plus something up to renormalization. But renormalization, this parameter lambda of t, is something that should be driven by an ODE, right? So this is exactly like coupling, like was said yesterday. It's like coupling a string to an infinite dimensional problem. This is exactly what these problems are about, extracting ODEs from the PDE and understand the coupling of all these guys all together. Okay, so what kind of singularity formation mechanism do I have in mind? I have exactly this in mind, this kind of singularity formation where indeed this parameter lambda wants to go to 0, possibly in finite and infinite time, and I want to understand when it is possible, how it happens, and what are the possibilities for the parameter lambda. Okay, this is typically the kind of question that we ask. So historically, of course, the mass critical problem, SC equals 0, in particular in connection with the cubic 2D and LS, that's the problem Michael introduced me to a bit more than 15 years ago. This is a very long story about what should be the structure of the singularity formation. It starts with this beautiful paper of Michael back in 1993 about the variational characterization of the ground state and the fact that if you are small enough in the critical norm and you have a sharp threshold, then you have to be a global solution. So there will be no singularity formation. And then there's been a lot of works devoted to the question of the understanding, actually, of this parameter lambda of t, so the speed of concentration that is here. And there's this beautiful story about the log law that was predicted by Landman, Papanicolaou, Sulem, and then a bunch of works further about, indeed, the fact that this is exactly the correct law and this understanding of the mechanism that is here. So this is really how some progress have been made on this problem is really through the understanding of this mass critical case here, SC equals 0. So I don't want to tell you about this problem today. I want to tell you about really going wild into the energy supercritical range. Okay, I don't want to be here. Maybe something I should say is that the analysis, be it formal or rigorous, it's not the point. To understand singularity formation in the SC equals 0 case, you use every line the conservation laws. I mean, it's absolutely fundamental that you have L2 conservation law and a conservation of energy above. This is a rigidity that you keep using all the time, right? So it's not like you're going to take this analysis and move it to the energy supercritical case. Something essentially completely different has to happen here, right? All right, so I want to be, so the typical supercritical range I have in mind, it's typically like take P equal 3 and D is 100, is 100, right? So there's no physics in here, it's not the point. What we're doing here is we're learning on what kind of phenomenon we should expect and what's happening in this zone and what are the differences, right? Hoping then to maybe be able to say something interesting on other problems. So I want to do that. I want, in this range over there, I want to see if singularity formation is possible. So for NLS, there is always, you know that something like singularity formation will happen. But you don't want to know if it happens, you want to know how it happens. And that's a different thing. And then there is something very important I want to say here. There is an issue of in which function class do you want to put yourself. You see, on these kind of problems, I mean, cooking up singular solutions, you can make solutions that look like they're forming a singularity. It's not that difficult if you allow yourself for solutions to do any type of behavior at infinity. That is, in some sense, it's not difficult to build solutions that look, in some sense, bad, that seems to have a singularity. But maybe it's the case that the singularity is there because maybe you didn't put the right behavior at infinity. So I don't want to see this guy. What I really want to do, I want to see a singularity emerge from a very nice, well-localized initial data. So typically, I want U0 to be C infinity compactly supported. Okay? I want to make sure that the reason why my singularity is forming has nothing to do with my data. I want to be in the function space where all the possible constraints of my Hamiltonian system that is L2 and energy are finite. And I want to make sure that the reason why I'm concentrating is really my equation that is taking this very nice wave packet and turns it into a monster. And I want to make sure that it's not my wave packet that was bad initially, right? This is an important point. And then I want to understand emergence of singularity from smooth well-localized data. And I want to understand whether the kind of things I'm thinking of, are these things generic or not generic? I mean, what's going on here? So how do you address such a problem? Well, so when you don't know what to do, you do what people have been doing on so many problems last century. I mean, really so many papers which just start like this. I don't know what to do, so what I'm going to do is I'm going to look for a bubble. You know, I look for the simplest possible solution I can think of. That is, I look for something that is, it's like a separation of variable, if you want. I separate time and space in some sense, and I look for U to blow up by just concentrating a fixed profile phi. So I'm just thinking of a given function, and I'm just write phi, say that phi is just some nice guy like that. This is phi. Then my solution U of t and x just takes this profile and concentrates it, say, typically at the origin, right? This is just, and I mean this to be exact. I mean, I really want phi not to depend on time. So if you do this ansatz and you ask for phi not to depend on time, you will realize that the only thing you can do is choose the so-called square root law for lambda. This is so-called self-similar scaling, right? So what you're looking for is a self-similar solution. All right, so let's do that. Then what you will do is that you're transforming your PDE into this nonlinear elliptic PDE here, stationary in time now, and this is what you have to understand. So this is so for Schrödinger this is not clear. I mean, what the solutions to this thing are. This computation you can do it for the heat equation as well, where things are better understood. And roughly the picture is as follows. So this is a very funny picture. So what you have is a so-called singular self-similar solution. So this is R. This is phi star of R. So what does phi star of R look like? Well, it's a very funny guy. It's a homogeneous self-similar solution. So it's the homogeneous self-similar singular solution. It's exactly equal to C over R to the 2 over P minus 1 and C is some number. Okay, this is an exact solution to my problem. Of course, it's a very funny one because it's singular at the origin, which is precisely my blow-up point. Okay, so it's very unclear what I should do with this guy. I mean, really, this is a very funny solution. Now you can ask, well, okay, this is bad at the origin. So you can ask, well, can I make this guy nicer at the origin? And the answer is, well, it depends. Immediately, well, again, so for Schrödinger, it's not so clear. The theory for the heat equation, I mean, this is all ODEs in some sense. This has been thought of like, because there is no variational structure, at least no obvious one attached to these equations. So actually, there is a numerology here. There is an issue of where is your exponent p. So you need p to be less than the so-called Joseph-Lagrange exponent. So which is, it has to do with, so it means that there is some value here, which has nothing to do with scaling, which has to do, if you want, with elliptic theory. There is some sort of numerology that arises here. And it tells you whether or not you can regularize this solution at the origin. So what I want to do is I want to put myself in this situation where I know that, in fact, this cannot happen. So I want P to be larger, this is PGL. So I mean that my expectation is that there should not be self-similar blow-up. Right? This is typically the situation I want to be in. I want to be in this situation where if I do this, well, essentially, I should not have a reasonable solution to that. Right? Again, making a theorem is a different issue, but this is exactly the situation which I want to put myself in, and this is a situation that occurs sometimes in other problems. So if there is no self-similar blow-up, what should I do? Well, I mean, this is something, sort of the intuition is the following. If your profile is not self-similar, then it should be stationary. So let's look at what stationary solutions look like. So this is the very interesting thing. So what is the stationary solution? So let me recall, so the self-similar equation is Laplace phi, say, minus 2 over p minus 1 phi plus y del grad phi plus phi to the p equals 0. Okay, the stationary, if you look for a stationary solution, it's just, I'm going to write it like that. It's Laplace q plus q to the p equals 0. Okay, so we find a solution to this. It's this ugly guy, which is homogeneous. But now, because this guy is homogeneous, it's very funny because, in fact, this term is dead because this is scaling. So in fact, my bad homogeneous solution, in fact, it's also a solution, right? And phi is a solution. Because it's a solution to both these problems, right? Simply because this term is 0. So phi is a solution to this equation, but it's bad at the origin. Okay, that's what I see from the formula. So now there is another one. That's the ground state. So there is another solution, not to the self-similar, to the stationary equation. There is another solution which you can construct from a very simple dynamical argument. It's the analog of my ground state, if you want, except that there is no mass because I'm energy supercritical. This is something well known. I started with the Talon-Thiobin soliton in the energy critical case. So what does Q look like? Well, it's a very nice bump. And actually, so it depends. And then actually, it's going to have some behavior at infinity. And at infinity, Q behaves like phi star. I mean, it means that this is a very funny situation. I have two solutions to my stationary equation. I have a bad one at the origin. I have a nice one at the origin. And both behave the same way at infinity. And this is fact of life, and this is, of course, I'm restricting myself to the radial case, but already just learning the structure of my solitary wave teaches me something non-trivial on the structure of the problem, right? And you have to work a bit to see this. I mean, there are some very nice ODE and Lyapunov functionals hidden behind this, but this is what I have. So what should I say about these solutions? Well, I should say the following thing. So what do I want to do? Okay, so let me just, let me erase this. So what do I want to do? I want to find solutions, U, that blow up like, say, some renormalization factor acting to leading order like x over lambda of t. Because this is typically what I learn, when this is typically what happened in other cases, like the mass critical case, and you sort of know from abstract ground that if something like singularity formation forms, well, you certainly expect that something like a stationary solution should kick in. But you have a problem here. You see, the problem is that my solitary wave, so take the one that's smooth at the origin. Okay, fine. Say P is free, and I am in dimension 100. So I decay like, say, 1 over R. Okay, so this is a disaster. This is huge decay. This is enormous. I'm very, very far from any sort of energy space of L2 norm. I mean, this guy is very bad. It's a very bad stationary solution in terms of function space. It really is. I mean, there is no way. I mean, if I really make some sort of ansatz, then it's going to be very, very bad, right? Because I want you really to emerge from a nice initial data. Okay, so in fact, what's going to happen to me is that I have a bad, if you want, it means that my candidate for being a profile is the stationary solution, but it's very bad. So however, I claim that it's okay. You can still, I mean, this will happen to you, and you will be able to show that there exists a blow-up bubble which have this kind of structure. But then what you have to learn is that what's going to happen is that the way, the zone in space where this identity is true, that is, where is it the case that you really look like the solitary wave? Well, that's sort of the heart of the analysis. That is that precisely this cannot be true forever, or in other sense, the perturbation I have to the solitary wave is going to be very good in some spaces, very bad in other ones, and this is sort of the heart of the analysis. So my claim is that even so, if you want, if I summarize, even so my solitary wave is bad, I claim that it's a good candidate for a blow-up profile, and I claim that, so this is what we did with Merle and Wolniewski in 2014, you can indeed find blow-up solutions that will, in some sense, form a bubble that will correspond to a concentration of this solitary wave, even though it's bad. And I claim that this happens for initial data, which are very nice, which actually are compactly supported. Okay, so this is indeed, this is exactly going to happen. Yeah, please?
Can I ask you, so can you also say that they are radial, for example? You work
Yeah. So I'm constructing at this point. So this is a radial construction. I'm definitely, this is the construction business, right? I'm not.
What do you know about gamma?
Oh, so you can compute everything.
Okay.
I can give you the ODE for gamma. I can compute it all. I mean, you can have I mean, I control these guys from A to Z. I can compute everything you want.
When you say it's proportional, you cannot quite.
Well, it's not proportional. It's equal to, and there is a correction.
No, for the lambda, I was thinking.
So I'm sorry. It's equal to, so it means that there is a constant plus a smaller of 1. So I can really put.
But you need a smaller of 1. You can't just take that value.
So I mean, you see, I compute that. So it's sort of part of the analysis to actually to compute this thing. This is the way it.
But the first relation.
I'm sorry. I think. Can you repeat the question? I'm sorry. Yeah. So the question was how I control this factor lambda of t here.
But the first relationship about u, this is stated. This is supposed to be true in some limited region of X.
Exactly. This is exactly the point, right? This is true somewhere. This is true, right? So this is what U looks like. So somewhere I'm going to do this in some region. This is what I'm supposed to look like, but it will not be there forever. Something else is kicking in here. It has nothing to do with this guy, and that's the heart of the matter. Okay, and let me say another thing. Another thing is that the blow-up rate that we find are quantized. They correspond to sequences. So alpha is a number that you compute from dimension in P, and K here is an integer that has to be large enough. So there is some sort of quantization here, which is connected to the fact that I'm asking for both smoothness and compact support. So let me not say too much about this, but let me say that this is a fundamental step of the proof, is to precisely understand what this kind of blow-up speed should be. So let me just make maybe one comment. I mean, in some sense, all these problems have nothing to do with singularity formation. They have to do with understanding of perturbation of solitons. And in fact, in this problem, it's really about interactions of solitons with radiation. This is exactly what's going on here. But let me, maybe because I have only 15 minutes left, let me say that, yeah, so a fundamental part of the analysis is to be able to compute the blow-up speed. So I mean, in all these problems, you need to understand the mechanism. So you need the formal heuristics. You need to understand what's going on here. Once you understand what's going on, then you need to do your estimate, close your estimate, and both steps need some work and some intuition on what is going on. So what I would like to do is explain you how we compute the blow-up speed. Okay, and I'm not going to do this on Schrödinger. I'm going to do this on a simpler problem, which I claim, which looks completely different, but I claim that what I'm going to do there is completely relevant. And in fact, what we're doing here is conceptually, I mean, seen from far enough, related. So let me show you a different problem, which is, well, again, has nothing to do with this a priori, but it's sort of correlated. So this is a problem which I learned from Maïr Hadjik, who was a postdoc in MIT when I was visiting there in 2012, and who came to me with this very nice boundary problem. So this is a very simple problem. This is a ball of ice. So I'm in 2D, say. So this is ice, and ice is at temperature 0. Okay, U is temperature. Outside, I have some profile of temperature, which evolves according to the linear heat equation. Right? There is nothing simpler. So it's like a two-phase problem. So here, temperature outside, but one of my phases is trivial. I just put 0 here. Okay, so it's a very simple problem. And of course, I need to connect. What I'm saying is that my ball is either melting or expanding. So I need to connect the value of U on the boundary. It just corresponds to the speed of the boundary. Okay, so initially, I start with some ball of ice, and I ask myself, what's going on and what kind of things can happen to me. And so the first thing you want to do really is start with the understanding of the radially symmetric problem. So I just imagine that I have some radius here, lambda of t. And then what's going to happen to me, this is the typical kind of phenomenon that you want to see. Initially, you start, so at least in spherical symmetry, what you start with is something that has size 1. So initially, my radius is 1. And then I want to understand how it can shrink, and at what speed it can shrink, and what can happen to me. Okay, so of course it should be simpler because it's a parabolic problem. But in fact, conceptually, It's deeply connected to what I'm going to say here. So to what we did on Schrödinger. So what's the answer? So there was a first paper on this problem by Herrero and Velasquez back in 2000, and then we revisited all this with Heuristics. So the answer is the following. So again, it's construction of example, spherical symmetry. So we can construct solutions. So these are melting solutions. And again, what we find is that the melting rate is quantized. And it's given by this awful numerology here. You should not care for these numbers. I mean, in some sense, these are not the right variable. This is what you get after reintegration. And what I want to explain you is what's going on here. Why can we compute this number? Where do they come from? And how am I supposed to do formally to understand that this is that in particular that these rates are quantized? So moreover, not only can we compute if you want melting rates, that is solutions where lambda goes to 0. So formally it's like a blow up. If you want high Sobolev norms of my solution would blow up here. We can also find solution, it depends on the data, that actually spread and that actually where the ball of ice extends, and it extends with very slow convergence rate, and against all this is quantized. So let me just give you a hint of what's going on here, because this is actually something very, very simple on this problem. Actually, we could see it because it's so simple on this problem, and once you see it there, actually now you can see it somewhere. So what's going on here? So what's going on is
do you maintain some conditions at infinity?
I'm sorry?
Do you maintain some conditions at infinity?
Well, I mean, you don't care really. I mean, everything is happening here. Everything is happening on
The heat equation is solved with you going to 0.
Yeah, I mean, typically, so the typical, what you would typically do, you would typically like to have finite Dirichlet energy, right? This is the typical kind of thing that you would like. So what's happening when you're melting here, what's happening here is that something wants to be, there is something, you see, you're becoming smaller and smaller, so what you want to do is zoom on this zone here and try to understand what's going on. So let's do this. Let's take a solution here, and I renormalize it. So I zoom on it, so I just change space, so y is r over lambda of t, so I'm really zooming on the zone when my ball is melting. And after renormalization, what you see is exactly this, so this is a very simple thing. So of course, the nice thing, it's a free boundary problem. By doing this, what I'm doing is I'm freezing the boundary. Right? So now instead of having a moving boundary, my boundary is at 1. But I have to pay for this differential operator. I don't have the heat equation. I have this sort of Fokker-Planck-like drift. I have this y dy term. And with this parameter a, which is directly related to the speed of concentration. Okay, so I want to understand this problem over here. So what's happening here is very clear. I'm facing this operator. So this is minus, so I have dsu minus the plus u plus a of s y dy u. Right, so do an adiabatic approximation. So what you're going to do is you're going to do some sort of adiabatic, that is slow time evolution variation of this. So to start with, say fix a. Say a is equal to 1. And actually, don't call it a, call it b. Okay, and look at this operator. So I have minus Laplace plus b y dy. I want to understand this thing. And of course, I have a boundary condition. I mean, the free boundary is its Dirichlet boundary condition there. So I have u of 1 equals 0. Okay, and I'm trying to understand what these things look, what is this operator and how I should understand it. Well, what I can do is I can renormalize it, so I can put the b to be of size 1. I'm just zooming, and then what it does to me, I can map this just by rescaling. I map this to minus Laplace plus y dy. But I give myself a boundary condition not at 1, but at square root of b. That's the way it shows up. Okay, so it's exactly like I'm having this structure here. So this is a new variable, say z. So I have this zone here, square root of b. So this is where u is supposed to equal to 0. I have the zone 1. And I look at this operator. Well, but this is very clear. So maybe I should call this variable here z. Well, so it's very clear. If you think of radially symmetric function, this is just one formulation of the harmonic oscillator. I mean, this can be conjugated to the standard harmonic oscillator. So of course, this thing has compact resolvent. You can diagonalize this operator in a suitable function space, and actually you know what the eigenvalues of this guy are. These are, I mean, the eigensets are the so-called Laguerre polynomial, and the eigenvalues of this thing are just lambda k is 2k, and the eigenstates are polynomial in Z. These are the Laguerre polynomials. So polynomial, of course, they are bad. They grow in space. But this is all I always have solutions that are bad in subspace. They always grow in space. But this is not too bad. I know how to handle them. But of course, I have a problem. My Laguerre polynomial, they don't, I mean, they correspond to the diagonalization of this operator, but in the solution, in the class of radial solution, that is with derivative equals 0 here at the origin. But this is not what I have. I have another boundary condition, right? It's exactly, it's like I'm having a thin layer here. It's like having a boundary layer. Right, so in fact, it's not difficult. So in some sense, the boundary layer, you can analyze what's going on here. And in fact, what I claim is that you can diagonalize this operator. You have to do your Lyapunov-Schmidt in a slightly, there's a perturbative analysis if you want that you can run here. It's completely elementary. And what you will discover is that this operator can be diagonalized. And it changes a little bit. So B is going to be a small parameter. It changes a little bit the value of the eigenvalue. Instead of having exactly 2k like you would have for your harmonic oscillator, you're shifting all this by a factor 2 over log B. This is what you get. This is really due to this change of boundary condition here to this boundary layer that shows up here once I've put it in the right variables. So I'm very happy with that because now this means that I can diagonalize for a given B, I can diagonalize this operator. Okay? So now I know what I want to do. What I'm going to do is I'm going to cook up an ansatz where V is going to be decomposed onto these eigenmodes with a bunch of value. But of course, what I know is that my parameter B now has to be allowed to evolve in time. Right? So this is exactly a typical situation, sort of a metastability thing, right? I'm really looking for a projection onto a given operator, but then I need to let my operator slowly degenerate by letting this parameter B goes to 0. And in fact, it's even a little bit more tricky than that. Remember, so when I renormalize, I have a parameter A, which is generated by the change of variable. This is generated by the speed of concentration. So I have an A here. So a priori, I should think, well, I should diagonalize this operator with an A. But this is a very bad idea because then at the end of the day, the operator will depend on time. So I'm playing this following trick here. I mean to put a B. I don't put an A. I put a B. I put another parameter. And then I will connect these two parameters with respect to this sort of Riccati equation here. It means that even though I'm seeing an operator with an A, I mean to put a B because this will treat the fact that my operator depends on time. Okay? Even though it's slowly varying, everything is small, and I need to connect things. And this is how it goes. So now once I have this ansatz, I just plug it in. Of course, my equation is linear. I mean, my PDE is linear. What's nonlinear is the boundary condition. So there are two things I can do. I can project into the eigenmodes. This will give me this equation with this log mode modification here, which are due to the fact that my eigenvalues are moved by my boundary layer. And then there is this relation here, which is due to the fact that I'm treating the time dependence of the operator. And the nonlinear term is here. This is the coupling between A and the values Bj, which emerge from my boundary condition. This is where I write that the derivative of my function is equal to the time derivative of the boundary, which is exactly given by this parameter A. Okay, so I do this ansatz. I project onto the eigenmodes. I write the time dependence here. So this is the slow this sort of makes the slow variable possible. And this is the nonlinear connection between, this is the dynamics on the boundary. So you look at this dynamical system, and my claim is that indeed this has solution. And so it means that you have, of course, you can think of solutions that live on the given excited state, right? So you can be either on the fundamental mode or the first excited mode, etc. So you can cook up solution to this dynamical system, which will exactly reproduce the blow-up rates that is here. So this blow-up rate here, just after reintegration. So this is the stable regime. It corresponds to exciting the fundamental mode, and this is stable. And this corresponds to all the possible excited states that are generated by this time-dependent ansatz based on this spectral decomposition here. Okay, so at the end of the day, I've sort of done, I mean, at the end of the day, this is something very simple. I've just diagonalized my operator, taking into account the fact that I am inserted in a moving frame, that is, I have this concentration effect. I diagonalize for a fixed parameter b, that is, if you want, by sort of freezing time, and then I let time evolve again, and it's precisely this time evolution. I let my operator crash, if you want, onto something that has just continuous spectrum. In this case, it's just the Laplace, and I see that this is possible only with this coupling, which exactly reproduce my blow-up speed. So not only does this give me a very nice heuristics, if you want, this has two things for me. First of all, it gives me a very nice heuristics for the derivation of the blow-up speed. And now, because I have a parabolic problem, and that's where we use fundamentally the fact that we have a parabolic problem, not only does it give me the heuristics, it also gives me, of course, a fantastic function space in which to work in which to work, right? Precisely, if you want, the function space associated to the spectral gap corresponding to this operator. So this corresponds to weighted norms with Gaussian weights, and which indeed not only can I formally construct my ansatz, I can also close my estimate in there, and that's where I'm using that I have a parabolic equation. I mean, doing this in the Schrödinger setting would be a very, very different issue. Here, things are really simplified by the parabolic structure. So this is really what you have to do. So you really need to close your estimates on the error in a suitable function space, and this is really simplified here using the fact that I have this very nice spectral structure. All right, so the outcome of all this is that we do now have some understanding of this instability mechanism of solitary waves, and in particular, this concentration phenomenon. And I should say that in the parabolic setting, I think that what I've just shown you here, so again, I'm showing this to you on this very simple free boundary problem. I claim that this goes much further than that. This can be applied to more problems. So in the parabolic setting, not only do we have a nice way of finding heuristic, there is really, at least for this class of problem, there is really a particularly efficient machinery there behind that can be used. So something also applies in the dispersive setting, but typically for Schrödinger, things are a little bit more complicated. And the last thing I'd like to say is that, of course, I'm showing you radial cases because it's simpler. There is no doubt about this. But there is nothing in this proof that bends onto the radial case. You see, typically in the literature, when you look at typically the nonlinear heat equation, then sometimes it's the case that you really very strongly rely on radiality being for maximal principal issues, or also being because there are very nice functional Lyapunovs that occur in this case. When we work with Schrödinger equation, this kind of things collapse. And if you want to work with more complicated problems, I think it's very important to have actually machines that can work also in the non-radial setting. And I think that we can make all these things work also in the non-radial case, which would be a first step to try and address more complicated problems. So conceptually, there is nothing in this approach that is really restricted to a specific problem. Of course, there are specific features of the equation, but sort of the global plan and strategy to attack the problem, I think, is fairly general. All right, thank you very much.
Okay. A couple of questions, just to be sure I'm clear on the relationship between the parabolic problem and the nonlinear Schrödinger. So, if I understand correctly, the scaling idea that you presented in some detail for the melting problem carries over something very similar. And then when you want to prove that you actually have a solution like this, for nonlinear Schrödinger, you must do something rather different because you don't have the parabolicity to to help you, right?
Exactly.
Okay. And so when you go non-radial, so your scaling picture was ODEs, right? And that was because you had a single one-dimensional eigenspace for each of these eigenvalues since you were radial.
Absolutely.
When you go non-radial, the essential difficulty would be that you would have a system of ODEs, as many as you have eigenfunctions, right? It's like constructing, so you have to do something similar to constructing the flow on a center manifold or something like
absolutely.
that, right?
This is exactly it. Absolutely.
Okay.
And now you can start saying that, man, maybe this guy will start interacting now in a different way. Of course, you can construct solutions do this, others do that. Maybe they want to interact. Maybe, but this is sort of, all this analysis is now prepared to see this, I think, and this can definitely be done. That's what I'm saying. Absolutely. No, so, let me put it this way. Constructing a blow-up solution in the energy critical case, in the parabolic case, this is a very interesting story. So the first paper that does this is really a breakthrough paper back in 92 by Herrero and Velázquez, 1996. It's an unpublished work. Don't ask me why. I don't know. What's in there conceptually is 20 years ahead of everyone. I mean, this is really a beautiful work. But now, if you want to do that, but the way they think of it is really, this is really funny. This is really funny. I mean, I'm telling you, I can show you this paper. It's really bizarre. And then the rigorous proof goes back to so there's a series of papers by Matano and Merle in 2004 and Mizoguchi in 2006. And what they do, they use something very special. They use that for the radial heat equation. You have Lyapunov functionals that are related to the maximal principle. And the Lyapunov functional is you count the number of intersections of your solution with, say, a given profile, say, the solitary wave of these kind of things. This is really a counting procedure. And it's like you have infinitely many Lyapunov functionals, if you want, you can play with. And they sort of give you a completely different functional framework, extraordinarily powerful, in which you can understand these kind of things. Right? So in some sense, I don't want to use any of this because this is not going to lead me anywhere if I want to sort of do different things or try to do Schrödinger or these kind of things. I mean, what does this mean? And moreover, not only it's not only a question of functional frameworks. I'm telling you, the way they think of the problem is very different. It's all about this singular phi star and what it looks like and etc. It's really so what the first thing we did in this work with Merle and Broniansky, we sort of put things together with what we knew with the theory of ground state and with sort of something which is more familiar. So this is sort of the first. So this forced us both to have new formal heuristics and a new functional frameworks more robust to address this. And now in the parabolic setting, if you want, I could do this problem with the Schrödinger tools. Okay, so but what do I do then? What does it mean? It means that every time I see dissipation, I throw it to the garbage because I know how to do proof without it in some sense, right? This is exactly what was going on in the beginning. We were doing parabolic problems by throwing away dissipation. Right, so now we know that we sort of have a simpler machinery here, which is much more efficient for parabolic problems, but it would not apply to Schrödinger. In some sense, if I had done this before Schrödinger, I would not know how to do Schrödinger. But it's the other way around. So it's good news in some sense. Things simplify for a parabolic problem, but for Schrödinger, it still is a Schrödinger equation. It's particularly.
I was asking about these non-spherical. Please wait for the microphone. I was talking about these non-spherical.
Yeah.
Excuse me. Yeah. So I was asking about the question asked earlier by Bob Cohn, which was what happens in the non-spherical symmetric case.
No, so in the non-spherical symmetric case, just take the nonlinear heat equation, supercritical, and make me a non-radial type 2 blow-up. This is not known. I mean, how stable it is, can you make me something truly non-radial? Don't put me trivial perturbations far away. I mean, this is, do me something that really analyzes the effect of non-linearity there, or maybe put me some terms that forces me to go away from radiality. This is not known. All the tools, all the parabolic
so even
tools.
in the parabolic case.
Yeah, even in the parabolic case, absolutely. Even in the parabolic case, absolutely.
Okay, that was my question.
One more question. But do you have an example of a problem where you need to go out of the radial class to produce, let's say you just want to produce this kind of blow-ups. Do you have an example where you need to go out of the radial class, or you can hope that it's going to work in the radial class all the time?
Well, I mean, for example, when we did KDV, you certainly had to go away from the radial class. I mean, so it was 1D.
One-dimensional.
It was 1D, but
yeah, okay, but it's one-dimensional going one way, so it's
yeah, but
special.
even if you start having things that start moving around, or you sort of need.
I mean, mean, if you wish, the question would be, does it prefer, you're going to have ODEs, even formally, and then you have to think, okay, finally, does it choose to be radial, or does it somehow prefer to be non-radial?
Well, but
and in the type 1 blow-up of semi-linear heat equations, it chooses to be radial. That was Herrera and Velasquez a long time ago. Here, depends on the ODs.
Yeah, no, but this is a fascinating question. Actually, they are very nice, in particular for supercritical type 2. There are very nice question about this. Can you find non-radial guys that actually would produce different blow-up speed? Does it exist? Can you see that non-radiality will produce new guys? Well, there are very interesting and fascinating problems actually in this direction. I'm not saying I know how to solve this. I'm saying that we have, of course, the first thing you want to do is understand the radial problem. It's simpler, no question about it. But what I claim is that the approach that we have does not have to stick to radiality. So now we are sort of prepared to start analyzing, the principle of the method is not stick to radiality. We're prepared to analyze more complicated problems, and maybe precisely this kind of behavior where you would expect that non-radiality is essential and produces new things. That's exactly what we're looking for.
Thank you again.
Thank you.